Well, hello, Honors Math 1. This is Mr. Roberts, and I'm going to be stepping through the solutions to the Chapter 2 study team test. I'm going to try and do this without a calculator, so if I feel like I'm fumbling on arithmetic, it's kind of by design. I just want to challenge myself to see how far I can get without touching the device. However, I recommend using a computational aid, especially to speed your work up and get through things quicker. So let's start with question 1. We were given 4 situations and asked to come up with the equation of the line that would match the information we were given. For part A, we were told that this line has a y-intercept of 3 and a slope of negative 2/3. Well, we know the rate of change, right? And we know our beginning point, our y-intercept, so we can write that pretty straightforward, right? It is y is equal to our slope, negative 2/3, times x, and then plus 3. And that's pretty much all we have. I can verify that because this is a y-intercept, I know on a y-intercept, right, the x value is always going to be 0, and our y value is 3. So I can plug that point in, and yeah, if I put 0 in there for x, it does make y 3. So, but I don't think I need that confirmation. Let's go to part B. In part B, we're told that the slope of the line is 3/4, and it passes through the point where x is 12 and y is 4. So we have this xy pair that we know it's passing through. So I'm going to start with a slope-intercept form of an equation. There's a slope-intercept form of an equation. I know that I'm going through a y value that's 4, so I can write 4 in place of y. I know that my slope was given as 3/4, and I can see that my x value was given as 12. So on this, oh, and it's plus b. So on this, I'm going to go ahead and do the multiplication. 3/4 times 12, I'll take 12 divided by 4, and I get 3. So I believe this is 4 is equal to, let me do that again, 12 divided by 4 is 3. 3 times 3 is 9, and then plus b. And if I subtract 9 from both sides of that equation, I get that negative 5 is the value of my y-intercept. It's b. So I could go ahead and write the equation of this line, and I'm just going to do it here. The equation should be y is equal to, my slope was 3/4. 3/4 times x, and then minus the number 5. Now, just a real quick check here. If I plug the number 12 into that equation, right, I should get the answer of 4. And 3/4 times 12, I just did that, right? That's 9. And 9, so this is 9, and 9 minus 5, 9 minus 5 is 4. So I can see that 12 does produce the correct output value. Let's go to part C. For part C, we're given 2 points, and we're told that the equation of this line passes through these points. So the thing that we need to know is, first of all, what's our rate of change? What's our slope, in other words, and what's our y-intercept? So if I look at this, I can see that my y value is going from 8 to 4. So the change there, if I want to, I can take 4 minus 8, and I get an answer of negative 4. So I can see that my y value changed by going down 4 units. I'll do the same thing, same direction for my x. I'll say x is at negative 2, and it travels to positive 6. So I'm going to take the negative 2, and I'm going to subtract. Oh, I'm doing that the wrong way. Let's go the other way. I'm going to take the 6, and I'm going to subtract the negative 2, which is the same as 6 plus 2. So I get that the change in my x value, right, my x value changed by, it increased by 8 units. So I know both the delta y and the delta x. So the slope of this line is negative 4 divided by 8, or negative 1/2. So this is a situation where the line is decreasing by 1/2 unit each time x increases by 1. Now we need to figure out our y-intercept. I don't have it, right? None of these points are a y-intercept, so we'll go ahead and figure out what it is. I'm going to use that second point, and I'll start with the same thing. Y's are equal to mx plus b. My y value is 4 from this point. That's the point I'm using, 4. And that equals my slope of -1/2 times my x value of 6. So I've got all the things in there. I just need to figure out what this is, my y-intercept. 4 equals -3 plus b. And if I add 3 to both sides, I believe that my y-intercept is at 7. Of course, I'm never satisfied with this answer. I need to kind of check it in some way, kind of interrogate the situation. So I'll write the equation. Y is equal to -1/2 times x plus 7. And what I'm going to do is I'm going to take my x values, plug them in, and see if I'm getting the correct y values. So when -2 goes in for x, I end up with -1/2 times -2, which is going to be +1. And yeah, 1 plus 7 is 8, so it checks for that point. For the other point, when I plug in 6, I have -1/2 times 6, which is -3. And -3 plus 7 is indeed +4. So I think we're pretty safe in stating that this is the equation of a line that will pass through both of those points. So for the last part of question 1, we have this table it's jumbled up, right? My x values are not in any particular order. The y values are a mess. So we still need to do the same thing. We need to figure out how much y changes, and we need to take and divide that by how much x changes. So if I look at my delta y, right, I can see y was at 8 and it goes to -25. So I can see it decreased a lot. I'll just take the -25 and I'll subtract the preceding value, 8. And when I do that, I get -35. No, I get -33. -25 minus 8 more is -33. So y, right, decreased by 33 units. I'm going to go the same way with this. This is the point I'm at. I'm starting at -6 and I'm going to +5. If I'm at -6 and I go to +5, I had to add quite a bit. In fact, mentally, I've told myself, oh, it's 11. It's 11. Let's go ahead and do this. So I'm taking the 5. That's the value where I ended up. And I'm subtracting -6, which is the same as 5 plus 6, which is 11. So my change in x is 11 units. So if I'm at -6 and I add 11, I get to 5. And if I'm at 8 and I subtract 33, I would get to -25. So now I know those two values. Let's go ahead and figure out our slope. Our slope is going to be the ratio of that change in y value, -33, divided by the change in x, +11. So it appears that our slope value is -3. So question is, what's our y-intercept, right? Fortunately, we know our slope. We know that rate of change. We just need to figure out our y-intercept. It doesn't matter which point I pick. I'm going to just randomly select this point. And if I use this point, I have an x value and I have a y value there. So same strategy as before. My y value is -4. Check. Equals my slope value. Equals my slope value. My slope value is -3. Check. And I'm going to multiply that by my x value. And my x value is -2. -2. So y equals m times x. And then plus b. Plus b. So if I'm looking at this, I've got -4 equals a +6 plus b. And if I take away 6 from both sides, -4 minus 6 is going to give me a y-intercept at -b. So I believe the equation of this line is y is equal to -3x and then -10. And if we just check it real quickly with a couple of the points, let's do it first of all with this point. So when I put -15 in there, I get -3 times -15, which is +45, and then 45 minus 10 is indeed 35. So it checks with this point. And it's nice to check with 2 because it's possible I could have come up with a line that just so happened to go through that point, but none of the other ones. So if I was going to check for a second point, let me just erase this and erase this. I'll go ahead and check for, let's do this point now. So we'll do this one second. So on this one, I've got a y, again, I'm just plugging in -6. So when I plug -6 in for x, this becomes y is equal to -3 times -6, which looks like positive 18. And then 18 minus 10 is indeed positive 8. So pretty satisfied with this solution. It's doing all the right things. Y equals -3x minus 10. For question 2, we were provided with two functions and with particular input values, and we said, hey, for these input values, figure out what comes out of these functions. So for this first instance, I'm going to go ahead and take 2 times something getting squared plus 18 divided by 12. And I really like to do this first and just put these placeholders for all the locations where I'm going to put my input value of x. My input value of x, the value that's going into this function, is 3. So I'll just place a 3 there. And then I just evaluate this expression. 2 times 3 squared, of course, I would square the 3 first, order of operation, giving me 9. And 2 times that 9 is 18. So my numerator is 18 times 18. 18 times 18 is 36. So what I have is 36 divided by 12, which I believe is 3. So fun fact, apparently for this particular function, when you give it 3, it spits a 3 right back at you. So the output here should be the number 3. For part B, we're given the function x squared minus 4. So here's a place for x to get squared, and then minus 4 times that same value of x. So we have two locations where we're going to be writing this number -4. One of them is here, and the other one is here. I really like doing it this way because now I can see clearly that what is getting squared is x, and x is -4. So notationally, I've written down this is -4 times -4, which is exactly positive 16. And then I've got -4 times -4, which is plus another 16. So 16 and 16 is 32. So when -4 goes into this function, it produces an output of 32. For question 3, we are given two functions in which we're told what the output is, and we're asked what is the input that would produce that output. So we're asked to figure out what x value is going in to produce, in this case, an output of 1. And what I like to do is just take the definition of the function, which is 7 minus 3 times the quantity of 2x minus 4, and set that definition of the function equal to our desired output, which is 1. And then just solve for x. So I'm going to rewrite this as 7. And then this is going to have to be a minus 6 times x and then plus 12. So you'll notice as I took these values out of the parentheses, they both were being multiplied by this -3. And then this equals 1. 7 and 12 is 19. 7, 8, 9. So I've got -6 times x plus 19 is 1. If I take away 19 from both sides, I get negative 6x is -18. Okay. And if I divide both sides by -6, I get x is -18 over -6, which I believe is 3. So when 3 goes into this function, right, when 3 is the input, it should produce a value of 1, and I can verify that, right? 2 times 3 is 6. 6 minus 4 is 2, right? This is the number 2. And then 2 times 3 is 6, and 7 minus 6 is indeed 1. So that checks rather nicely. X is the input that will produce an output of 1. And then for the second part of this equation, we're given the function f of x is defined as just 3 times x. So the definition of this function is take whatever x is and triple it. So that's the definition. I set it equal to the desired output. And if I divide both sides by 3, I get x is 12 over 3. X is 4. And of course, I can see that now, and probably I could see it before. But I like going through this process anyway, so it's very reassuring. Yes, if the input value to this function is 4, when 4 goes into this function, it produces an output of 12. Because 3 times 4 is 12. Next, we're given a series of monomials, and we're asked to simplify them. I had an interesting conversation with two different students in two different periods, and one of them dealt with this 7 sitting outside of here, and the just following this pattern of, oh, do both the x squared and both this y to the negative fourth get multiplied by the 7? And that's understandable because we do know that we distribute multiplication across addition and subtraction problems. But in this case, it's just 3 things that are being multiplied together, right? It's 7 times something, and then times something, and then times something else. So it doesn't. If you're ever at a point where you're like confused and you want to think about this, I like to just kind of quickly come up with a numerical problem. So if I had 7 times 3 times 2, I know that that's just 7 times 6. That's one way to think about it, right? It's 7 times 6, which is 42. Now, if I was multiplying both the 3 and the 2 by a 7, all of a sudden that would become 3 times 7, 21 times 14. And I guarantee 21 times 14 is much larger, right? So this is not true at all. So I'm just multiplying 3 things. And it's probably worth pointing out why we think this at all. It's because we've seen this, right? If I have 7 times the quantity of 3 plus 2, right? This is a different story, because what I have here is it is 7 times 5, right? 7 times 5, this is 35. And it turns out if I multiply each of these terms, I have a term of 3 and a term of 2. If I multiply both of them by 7, what do I get? Well, 3 times 7 is 21, plus 7 times 2 is 14. And when I add those values, right, 21 plus 14 is indeed 35. So we can understand the confusion. The important point to take note of is that there's a difference between factors, right? 3 and 2 here are factors. They're being multiplied to produce a product. And over here, 3 and 2 are terms. They are being added to produce a sum. So we do distribute across terms, but we do not, there's only one 7 in the other case, right? There's not a 3 times a 7 and a 2 times a 7. It's just 7 times the thing. So come back to this. All of that said, right, I just have a single value of 7 that's going to lead this. And then it's just multiplication. I've got x to the 2nd times x to the 4th, which is going to be x to the 6th power. And then I have this y to the negative 4th times y to the positive 9th, which is going to be y to the 5th power. So that should be our answer for part A. 7x to the 6th, y to the 5th. Let's jump to part B. On part B, I'm just going to go ahead and do this. This is 25. I've got a factor of 5 in the bottom. I can rewrite 25 as a 5 times a 5. These are factors. And then times, I'm going to note that in my denominator, I've got an x cubed. So I'm going to match that in my numerator with another x cubed. Of course, what I've written down is not equivalent to what I started with. So I'm going to go ahead and put 5 more factors of x in the numerator. Now I can see my numerator is exactly 25x to the 8th power. And as I say that, I'm saying it, but I'm reading this. This is 5 times 5, which is 25. X to the 3rd times x to the 5th is exactly 25x to the 8th power. And the denominator is still 5x cubed. What's convenient about writing this way is I can clearly see that I have a giant 1 in the form of 5x cubed over 5x cubed. So this simplifies to, in the numerator, there's a factor of 5. And there are 5 factors of x, and we like to write that as x to the 5th power. So that's 5x, 5x to the 5th power. For part C, I think I'm just going to note to myself right off the bat that this is b to the 2nd power. So I'm going to rewrite that. The whole thing I'm just going to write now is, well, let's do this. I'm going to write an a to the 3rd power. And then in my numerator, I'm going to write an a to the 3rd power. I need two more factors of a, so I'm going to write a squared. So what do I have here? I've got a to the 5th over a cubed, and then times, this is going to be b to the 2nd power. That's what a to the 5th times, or I'm sorry, b to the 5th times b to the negative 3rd is. It's b to the 2nd. In my problem at this point now, you can see that there's a value of 1, and what am I left with? I'm left with a squared b to the 2nd. So a squared b to the 2nd is equivalent. A squared times b squared is equivalent to the original expression. And the final problem here, there is something that's getting cubed, right? What is getting cubed is the 2x to the negative 2nd. So I'm going to take, the numbers are small enough, I'm going to go ahead and take and write out 3 copies of that. So, oops, not cubed. It's a 2x squared times another 2x, I'm sorry, to the negative 2nd times another 2x to the negative 2nd. So if I was to, write this, this is the expanded form, but I can go ahead and do the multiplication. 2 times 2 is 4, times another 2 is 8. And then I have x raised to the 1, 2, 3, 4, 5, 6, x to the negative 6th power. When we're asked for simplified monomial, simplified expressions, we do not like to have negative exponents as part of the answer. It's partly historical, and it's also easier to work with. So when we see this, we always remind ourselves of something. Just this simple case, right? 2 to the negative 1st power is 1/2. So that observation lets me kind of remind myself, oh yeah. If I have something to a negative power, it's a reciprocal. So I can write this as still 8's in the numerator, right? Because the 8's not being raised to the negative 2nd, just the x's. 8's in the numerator, and my denominator, I've got x to the 6th power. And coincidentally, if I was to pick any value of x, 0 is a bad value, 1's a bad value for test purposes, but pretty much any value of x, any value of x, even 0 and 1 would work. The reason why 0 and 1 are bad test values is it just so happens I could be wrong, and 0 and 1 often work anyways. But what am I trying to say? I'm trying to say that if I took this expression and I stored a value like, say, 2.3 in my calculator for x, it should be the case that if I evaluate that and look at the resulting decimal, I should get the exact same thing as if I were to plug, leave x as 2.3 and evaluate this expression. This is a simplified version, and the heart of understanding there is that this expression and this expression will always produce the same outputs for any given x input. I guess fun fact, 0 is not in the domain of that if I was to write it as an expression, because division by 0 would be a problem. But I'm talking needlessly. Let's move on to question 4. And by question 4, I mean, of course, question 5, because we just did question 4. So just real intentional, I'm just going to go around and write the 2x plus 1. And then plus, and I'm going to distribute this. This is going to become 4 times x, and then 4 times negative 2 is going to be negative 8, and that equals 11. I'm going to combine these. They're like terms, and I'm going to combine these. They're like terms, and they're on the same side of the equation. All these are on the left-hand side. So I'm going to get 6 times x, and then minus 7 equals 11. If I add 7 to both sides, I get 6 times x equals the number 18. And then dividing by 3, I get that, dividing by 6 rather, jumping ahead here, 18 divided by 6 is 3. So if I was going to confirm this answer, 2 times 3 is 6 plus 1 plus, if I put a 3 in there, 3 minus 2 would be 1, so this should be a 4. And if I combine those, yes, 6 plus 1 is 7, plus 4 is 11. So this value, when x is 3, it does satisfy that equation. That's why we call that a solution. One more of these, we're asked to solve this linear equation. So I'm going to just rewrite it. There's a 4x and then minus 3x minus the number 6. So notice I was multiplying negative 3 times positive 2. That became a positive 6 plus 11 equals 6 times x minus 30. So when I'm doing problems like this, I generally avoid touching the original expression. I don't like doing that. What did I do here? I rewrote the left-hand side and the right-hand side by using the absolute simplest form of the thing that we call the distributive property. If I combine like terms on the left-hand side, I've got a 4x minus 3x, which is just an x. And I've got a negative 6 plus 11, which should be plus 5. And on the other side, it's 6 times x minus 30. I'm going to subtract x from both sides. 5 is 5x minus 30. I'm going to add 30 to both sides. 35 is 5x. And then finally, I'm going to divide both sides by 5. When I do, I get this. And it turns out that 35 divided by 5 is just the number 7. 5 times 7 is 35. If I come back up and I place 7 into that as a check, 4 times, what did I get? 7? 4 times 7 is 28. And then 7 plus 2, 7, 8, 9 is 9. And then minus 3, that 3 times 9 is 27. So I've got 28 minus 27 and then plus the number 11, which looks like 28 minus 7 is 1 plus 11 is 12. So the left-hand side is 12. Question, is the right-hand side the same? When I plug 7 in here, what do I get? 7 minus 5 is 2, and 2 times 6 is 12. So this is absolutely the solution because it makes both the left-hand side and the right-hand side equal to 12. And that happens when x is the number. For question 6, we were provided with values of a, b, and c, and we were asked to evaluate 2 different expressions given these values. So these are important. We will refer to them because we need to know what those values are. Let's look at the first expression. It's here. It says 2 times the quantity of a plus b. Now I can look at a plus b and I can see that that's negative 1. Right, I'm just looking at these two together are negative 1. And negative 1 plus 5. Negative 1 times 2. I have to multiply by 2. Negative 1 times 2. Now at this point, I'm talking to myself and I'm being careful, but I almost did miss that too. So one of the things I like to do is just write this down, right? I have plenty of time to do this. So, excuse me, I've got the value of 2 times, here's a place for the a, negative 3, plus b, which is 2. And then I'm going to add 5 to that. In my denominator, I'm going to take c, which is apparently 2, and I'm going to add 1 to that. So in the numerator, I start with these grouping symbols first. Negative 3 plus 2 is negative 1. Negative 1 times 2 is going to be negative 2. So the numerator is a negative 2 plus 5 over the number 3. Negative 2 plus 5 is 3. I've got 3 over 3, which looks like 1. So expression A, right, with the values of the variables a, b, and c we were given would equal 1. Let's go to expression B. B says that we need to square a and b. There is a misconception that I'd like to address now. Those of you that are watching it, hey, you're in for a fun treat. When I have b plus c and I'm asked to square it, some of us are under the impression that that's the same as b squared plus c squared, and it is not. And I, again, understand the reason why there's some confusion. It still goes back to these are terms, versus if I had b times c and I was squaring that, that would be b squared c squared. However, we don't have that. We have 2 different terms here, things that are being added. And I need to evaluate that addition first. Later on, when we talk about multiplying things that look like b plus c times b plus c, literally I have to do this. I've got a b plus c times another b plus c. And as we'll learn, that is not b squared plus c squared. It is not. So I'm going to be very careful here and go ahead and take my values of b, 2, and my value of c, 2. And I'm going to add those, which gives me 4, and then I square it and I get 16. So this is 4 squared or the number 16. If you were to do this the other way and square those individual values first, what would you get? You'd get something too small. You would end up getting 2 squared, which is 4, plus another 4. You would end up getting 8. And I just want to be really clear, these are not equal. This is not the number 8. So I added those two values, and then I squared the result. I get 16. I'm going to add an additional 4 plus an additional 4, and then I'm going to subtract 5 times c. C is 2, so what am I looking at here? Just subtracting 10, I think. Did I do that wrong? No. It's going to be plus 5 times 2. So I've got a positive 4. Ooh, no, this is minus 10, minus 10. So what I'm looking at, I believe, is 20, 16, 17, 18, 19, 20, minus 10, which is, I believe, is just 10. So for part B, the answer was 10. That's the value of that expression. B, the quantity B plus C squared plus 4 minus 5C. That's the value of that expression when A is negative 3, B is 2, and C is 2. Second to the last problem, we are given an expression, 125, we are given an expression, it's actually a rate, 125 gallons per 1 week, and we're asked to convert that into gallons per hour. And you can see that the problem is done for us, right? It's complete. We just have to know how to go through and cancel out units and then find the correct value. So one of the things I want to point out is, yes, if you're looking at this, this was set up so that I took the 125 gallons per week, and then I multiplied it by the fact, let me get this highlighter, I multiplied it by the fact that 1 week is the same as 7 days. Now I put the 1 week in the numerator and the 7 days in the denominator. And then I did the same thing with to get rid of days. I know that 1 day is the same as 24 hours. So I brought that giant one in. And we can see exactly what happens, right? All of our units are canceled except for we're left with the units of gallons in the numerator and hours in our denominator. So we know what units we're talking about. What's the number? Well, the number is 125 is the numerator divided by 7 times 24. And the units there are gallons per week. Oh, no, gallons per hour. And unfortunately, I said I'm doing this test without a calculator. So there's no way I'm going to take and divide 125 by 7 times 4 manually. It would just take, it'd be too painful. But I believe it was if I'm guessing, I believe it was 0.74. This is just from memory. When I made the answer key, I'm pretty sure that's what I got. 0.74 gallons per hour. So 125 gallons per week is almost close, 3/4 of a gallon, 3/4 of a gallon per hour. Certainly every 2 hours, it would be about 3 gallons if we added those up. All right, our last problem involves dimensional analysis also, and it revolves around the Hubble Space Telescope, which is quite dated now, right? There's cooler cats on the block, although it's still doing they're still doing some science with Hubble. But the Hubble Space Telescope travels around the Earth at a speed of 308,000 inches per second. And we're asked to convert this rate into miles per day. It says show all ones needed to make this conversion and use the technique we've discussed in class, dimensional analysis. So this is a good chance to kind of just go through this. So I've got this large number, 308,000, and that is inches per each second. And I'm going to have to do this twice, once for time and once for distances. I'm going to do it for the time first. I want to get my units into miles per day. So I need to turn seconds into days. So to do that, I'm going to start with the fact that, well, there are 60 seconds in 1 hour. No, 60 seconds in 1 minute. Thank you. That's equal to 1, right? My justification, why can I multiply that by that? Because that's equal to 1, right? 60 seconds is the same amount of time as 1 minute. I can multiply that by the fact that there are 60 minutes in 1 hour. Why can I do that? Because it's the same amount of time, right? 60 minutes is the exact same amount. So that's a giant one also. And then finally, I can say, what do we want per day? There are 24 hours per 1 day. So at this point, a bunch of things go away. Let me grab a highlighter here, and I'll just highlight these in green. Seconds are gone with seconds. Minutes gone with minutes. Hours canceled with hours. So we're now looking at inches per day. The numbers are all there. We're going to need the numbers in a minute, but let's keep going with the dimensional analysis and take this for the next part where we need to transition inches into miles. And up on the whiteboard, I did have some possible ones that you may have needed if you weren't familiar with these. One of them is that in a foot, there are 12 inches. So I can say, look, I'm going to put 1 foot in the top in the numerator, and I'm going to put 12 inches in the denominator. The reason why I chose to write it this way and not the reciprocal is because I have inches in the numerator, and I need those inches to cancel. So I put inches in the denominator. The next thing I'm going to do is I need feet to go away. So I'm going to put feet or feet in the denominator, and I can go 1 mile. 1 mile is 5,280. 5,280 feet are in 1 mile. So at this point, if I continue with the time-related dimensional analysis, right, you can see that, well, this inch is going to cancel with this inch, right? This foot is going to cancel with this foot. And the only units that we have left in this entire problem are we've got miles in the numerator and days in the denominator. So we're looking at a rate of miles per day. Now it's on to a question of what's the number. Well, our numerator had this 308,000, right? 308,000 multiplied by a 60 times another 60, and then times 24. Everything else was a 1. In the denominator, we have this fairly large, let's see, what do we have? In the denominator, we've got a 12. We've got a 12, and we've got a 5,280. And that is the arithmetic I need to do. I need to be really careful and make sure I know what the numerator is, and then divide by the denominator. A lot of times the error would occur if you were just doing the numerator and then you did divided by 12 times 5,280. What happens is if you don't use the parentheses, your calculator will immediately divide by 12, get a result, and then multiply that by 5,280. So these parentheses are kind of important. They're making sure I'm taking the whole numerator, dividing it by the product of the denominator, or the factors in the denominator. And when I do this, again, I don't have a calculator with me. I'm pretty sure it was 420 something. Let me pause and look at my answer key. Okay, this is not mental math. This is me literally just looking at my answer key. But apparently this is equal to 420,000 miles per each day. And please, I encourage you to use a calculator for that task. Let it do the arithmetic, you do the math. All right, guys, that's it. That's the Chapter 8 study team test. I hope you found this helpful and that you use this in preparation for the individual test on Thursday in class.